right, so page 220, second half of 3.1, looking at the natural base E on 220. All right, so just for review, you might remember that we had talked about two different types of exponential functions in the first half of this lesson. We had talked about the decreasing function y equals a to the negative x, or another way of thinking of that is 1 over a to the x. So whichever way you think of that, when you do a to the negative x or 1 over a to the x, you're going to get values in between 0 and 1. You're going to get fractions, right? Like if you have 2 to the negative x, that's the same thing as 1 over 2 to the x, so that's going to give you fractional values. The other scenario was when we had y equals a to the x, where a was a number greater than 1. And so when we put those two scenarios together, that covered all of the exponential functions, because we had said an exponential function was something in the form of y equals a to the x, where a was greater than 0 but not equal to 1. So here are the values between 0 and 1, and here are the values greater than 1. We had two landmarks for our exponential functions. Unless it's been shifted or reflected or something, shrunk or stretched or something, then we were going to have a y-intercept at 1 and a horizontal asymptote at 0. We also had a continuous function. Both of them had a domain of all real numbers and a range of 0 to infinity. And the significant difference was that the negative function was decreasing and the positive function was increasing. All right. What we want to look at specifically today is the natural exponential function. The natural exponential function is something in the form of y equals e to the x. Now, e is a number very much like pi. It's a number that is non-repeating, non-terminating, shows up so often in nature, we call it the natural base. And we put it in our exponential function, it makes it the natural exponential function. You might also remember we have a natural logarithmic function. That'll be coming up in another few sections. E is non-repeating, non-terminating. It gets its definition from if I were to do 1 plus 1 over x to the x, and I kept putting larger and larger and larger values in for x, then I would continually get closer and closer and closer to this value. Now, when I look at it on my graphing calculator, it's going to look like it's repeating because it goes 2.718281828, but then after that it deviates. It is irrational. It is non-repeating, non-terminating. So just like pi, we assigned it a letter so that it would be easier to deal with. It's like we gave 3.14, we gave that the symbol pi so it's easier to work with. We gave this the letter E, so that it's easier to work with. So when I see y equals e to the x, that literally is y equals 2.718 ... to the x. If I go back and I compare that to these two scenarios, that's just this scenario. It's the increasing exponential function. It has a y-intercept at 1, it has a horizontal asymptote at 0, it has a domain of all real numbers, and it has a range from 0 to infinity. So it's actually something that we've already learned. It's just a specific case of what we've already learned. So just like we had done y equals 2 to the x and y equals 3 to the x, this is just in between, y equals 2.718 to the x. I love the exponential function, just like we've talked about so many things before when we talked about pi and we talked about the Fibonacci sequence. I love it when we find a really random number like this, that the probability of it showing up just a couple of times would be extreme, but the probability of it showing up everywhere is just inexplainable. And so to me, I love that when we see that type of thing happen, that it just gives us further evidence of God as the creator, and of God who is also an amazing mathematician whose favorite subject is math. Just is. That's the way it is. All right, so let's throw a couple of these in our calculator. Grab your graphing calculator if you would, please. Graphing or scientific, it doesn't really matter. So there are two different places that you have an E button on your calculator. If we wanted to do e to the 1, or we just wanted to remember what e was equal to, Right over here, you'll see above your division bar, you have an E button. If I hit E, it'll remind me of what that's equal to, but I also could raise that, like the first one they asked me to do is E to the -2. So I could definitely use that button and then use my caret key to raise it to some type of an exponent like -2. The other place that I have that button is right over here, right above ln. And that one is already e to the x, so if I'm raising it to an exponent, it just saves me a keystroke. Because, for instance, if I want e to the second, then I have one less button to have to push. So if you just want a plain e, you might want to use the one above the division bar. If you're going to take e and raise it to an exponent, then you might want to use the one that is above ln. Now, we should be able to do basic graphs of the exponential function where we shifted and reflected and that type of thing the exact same way we did on the first half of this lesson, because the exponential function is exactly, the natural exponential function is exactly like the increasing exponential function that we looked at in the first half of this lesson. But if they give me something a little more elaborate, like they do in example number 7, then they're going to ask me to graph that on my calculator. So let's go to y equals and put in what they give us there. They give us 2e to the 0.24x. 2e to the 0.24x. And I'm going to start with a zoom 6 as my standard with 10s all the way around. And so there's the graph of that function. So even though it has been altered, you can see it's got the 2 out in front of the function, which we know a 2 out in front causes a vertical stretch. That's why it's not crossing at 1, it's crossing at 2. That's why it lost one of its landmarks, because it's had that stretch. And we also have a number in front of x that's going to be skewing the graph, but you can see it still has that same basic shape of the increasing exponential function. So we should be able to graph e to the x by hand. We should be able to do horizontal and vertical shifts, and we should be able to reflect it, but if it's something more elaborate like we just saw there in example 7, then we'll throw that into our calculator. One of the most practical lessons that we learn all year long is applications of exponential functions. They talked to us on page 222 about compound interest. One of the most familiar examples of exponential growth is that of an investment earning compound interest. And so the formula for compound interest is on the bottom of page 222. It's A, your amount when you're done, is equal to P, your principal when you begin, times 1 plus R, that's going to be your interest rate, and we're going to write that as a decimal, divided by N, where N is the number of times each year that your investment is getting compounded with interest. This N is the same, and T is your time in years. So there are some things, let's say that maybe you have a savings account. There are some things that are compounded monthly. You get a statement every month and they show you, okay, if we were going to pay you 1% interest, which for most banks is a big stretch for a savings account, but if we were going to pay you 1% interest, we're going to pay it over the course of 12 months, so we'll take that 1 and divide it by 12, and we'll compound your interest once a month, so that would be 12 times a year, right? There are other things that might get compounded quarterly, like maybe you have a stock or something that's in a retirement fund or a 401k or something like that, and it gets compounded quarterly. That's 4 times a year. If you had something that was compounded annually, that would just be 1 time a year, or semi-annually, that would be 2 times a year, or daily, that would be 365 times a year. So that's why they leave that N in there, so it leaves it open to the number of times that something is compounded each year. So for example number 9, it says a total of $12,000 is invested at an annual interest rate of 9%. Find the balance after 5 years if it's compounded quarterly or if it's compounded monthly. Okay, so we can start off with, if it's 9%, I need to rewrite that as a decimal. What is that as a decimal? Yeah, 0.09. So we can come down here, we can say, okay, what's our principal? How much were we investing? Yep, a total of $12,000 is invested. So my principal is $12,000. And then we've already said that our rate would be 0.09. If it's quarterly, how many times are we compounding it a year? 4. So N is going to be 4. And they asked me to find the balance after 5 years. So our time in years is going to be 5. So once we get this set up, the bigger trick is typing it into your calculator correctly. So definitely grab your calculator and throw this in and make sure that you're getting the correct answer. But you can see, man, we did pretty well because we've made over 50% more from what we started with in just 5 years. All right. If instead that had been compounded monthly, what's the one thing about that that would change? N would change, right? So instead of it being 4, it would be what? 12, right? So we could do the same thing. It's still the same principal. It's still the same rate. It's just that N is 12 going for that 5 years. So again, be sure you throw that into your calculator and that you're able to come up with that correct value. Now, one thing you'll notice is there's about a $60 difference in price here in the total amount that I have at the end. My principal did not change. My rate did not change. My time did not change. The only difference here is the number of compoundings. So the more often they compound this, the better I'm going to do. By the way, for some reason, it tends to bother people when you have something like 9.5% interest or 9.5% interest. You're still going to treat that the exact same way. The same way you changed 9% back here where you said, let me back my decimal up 2 places. I'm just going to do the same thing here. Move my decimal back 2 places. So 0.095. So even if I get a fraction or a decimal or something, don't let that bother you. So that's compound interest. Another way that interest can be compounded is something called continuously compounding interest. And for continuously compounding interest, you let the number of compoundings N increase without bound. And so to do that, I need a totally different formula. The formula for continuously compounded interest is A equals PE to the RT. So A is still the amount I'll have left at the end. P is still my principal. E is that natural base that we talked about earlier today. R is my rate. T is my time. So if this is compounded more often, I should end up with more money, right? So I'm going to have the same principal, the same rate, the same amount of time. The only difference is the number of times it's compounded. And sure enough, I do end up with more this time than I did in either of the previous 2 scenarios. All right, so let's look at a couple of real-world applications that are not in our textbook here. All right, one of the best ways that you can take advantage of compound interest is with some type of a long-term savings account, like a retirement account, a 401k, a something along those lines. Because here's how compound interest works. Let's say that you got $1,000 for graduation from college from grandma. And so at age 21, when you graduated from college, you put that $1,000 into your company's 401k, and let's say that it was making 5%. Now 5% is probably very conservative here because most 401ks are going to have good years and bad years, but the net overall increase is typically going to be higher than 5%. So we're being conservative here. The first year, at the end of year 1, you're going to have your $1,000 and you're going to have your 5% interest. So 5% of $1,000 is $50. But at the end of year 2, you're not going to get $50 in interest. If you did, you'd have $1,100, right? You got $52.50 in interest. Because what they did was they paid you 5% interest, not just on your initial investment of the $1,000. They paid you interest on the full $1,050. They paid you interest on the interest. That's what compound interest means. when they're paying me interest on top of the interest. So that if I put this in here at age 21 when I graduated from college, and I took it out at age 65 when I wanted to retire 44 years later, that $1,000 would have grown to $8,557. That's a big return. I mean, literally like 8 times, more than 8 times what I started with, right? The key here is time. The longer I can leave that in there, the longer it can compound and I can get interest on top of interest on top of interest, the more that's going to grow. So let's say that you have an investment of $5,000 a year for 10 years only, and then you stop. So you put $5,000 a year in for 10 years only, so that means your total investment is $50,000, right? If you were to put that investment in from age 25 to 35, and this is assuming an 8% increase, so again, that's I think an easy thing to match. If 25 to 35, those 10 years is where you put your $50,000 in, by the time you finish at age 65, you're going to have $787,000. But if you put that same $50,000 in from age 55 to 65, you're only going to have $78,000. The principle is the same. The rate is the same. The only difference is the time. Because this first investment has had time for the miracle of compound interest to occur, to get interest on top of interest on top of interest. So when you get your first job, when you get out of college, you're thinking about, I have to buy a car and I have to pay off student loans and I have these things that I have to take care of. You have got to start putting money into a 401k. Even if it is only $25 a paycheck, you put in whatever you can while it has the biggest amount of time to grow, because it is going to make a huge difference in the end. If you wait until the mortgage is paid off and the kids are out of the house and you actually have a few extra bucks to throw at a 401k, it's too late. Okay? So time is of the essence. All right, so we have talked about how you can take advantage of compound interest, the positives, the power of compound interest. There are also huge dangers in compound interest. Where can it kill you? Credit card companies have some of the biggest buildings in the world, and they are some of the richest companies in the world because they take advantage of compound interest at our expense, right? So let's say it's coming up on Christmas and it's going to be one of your last Christmases at home, and so you decide you want to have a really nice Christmas for your family this year. You want to get your family some nice gifts and, your friends some nice gifts. So if you have not gotten one already, you will very soon start getting credit card offers in the mail. And so you get a credit card offer in the mail and you open it up and you decide you're going to charge $1,000 and you're not going to put any more money on it ever again. Okay? So here's what's going to happen over the course of a year. Typically, a credit card interest is going to run about 23 to 26%. So we'll go 23. Now they might have first 6 months you get 6.9%, and then after that it's going to jump up. But typically running something around here. So we're going to take that 23% and we're going to divide it over the course of 12 months, and they're going to compound it annually. Okay? So that's about 2%, a little less than 2% a month is what they're compounding, right? So in December, you put that $1,000 in, they run about 2%, a little less than 2% on that. And so they're going to charge you $19.17 interest. So the next month, you pay $19.53 interest. And you're like, wait, why did it go up? Because they charged you 23%, not just of the $1,000, but of the $1,019.17. They charged you interest on the interest. And by the time you get to December, you would be paying almost $24 in interest. And if you add all of those interest payments up, you'll now owe $255 more than what you started with. That's 25.5% interest, right? I thought it was only 23%. The difference is the compounding. It's the interest on the interest. So, you go to college, and you've got to buy books, and your roommates would really like it if you would buy deodorant and toothpaste. So you buy just the bare necessities. To buy your books for the semester and to buy like the necessities from Walmart that you need. We're not talking about making late night fast food runs and all that kind of stuff. We're just talking about bare necessities. You are going to need about $1,000. That might not even cover it, but we'll try that. $1,000 a semester for books and just very basic expenses. All right. So assuming we can actually get out of college in 4 years, which is tough sometimes. I get out in 4 years and I have $8,000 in credit card debt. And I'm going to start paying that off, and I'm going to pay exactly what they tell me to. All right. The minimum payment that you can make is typically going to be one of these two things. It says your account agreement or your monthly statement will typically say something like your minimum payment is 3% of your balance or $25, whichever is higher. So you're going to pay about $25, or 3% of this would be around that same amount each month until you pay that off. How long, just approximately, how long do you think it's going to take you to pay that off? Yep, you just pay the minimum. That's all. You're not paying it late. You don't have any fees or anything like that. You're doing exactly what they tell you to do, paying the minimum balance every month. What? Couple of years, okay. Like 3, 5, 10 years. 10? Really? I think 10 years? Do you think that's a little high? 10?
I'll say 15.
15? Cool. How about 22? 22 years. Hello, I'm 43 years old by the time I finish paying off my college credit card from when I graduated at 21, right? And by the time I finish paying that off, I have done everything they told me to do. I paid the minimum payment every single month on time, did exactly what they told me to do. I have paid, hang on, $13,000 in interest on top of the $8,000 that I borrowed. I paid more in interest than the money that I borrowed. That is how they make their money. That is the trap of compound interest. Okay, so that means that credit cards are evil and they're of the devil and I should never have one, right? All right, if you have taken our Dave Ramsey course here at school, because we do offer that as part of our business program, you know that Dave Ramsey is the big scissors guy with cut up all the credit cards kind of thing. And my husband and I have gone through the whole Dave Ramsey course, and I love Dave Ramsey stuff. That being said, I have 2 credit cards in my purse, but I have some rules for those credit cards. I don't like to carry a lot of cash. If I have a $50 bill in my wallet and I break that 50, I swear it's like gone, and I don't know where it went. And I'm sitting there going, where did I spend that money? Where did it go? So if I have my credit card, at the end of the month I get my statement. It breaks it down into nice, happy little pie charts. I can see exactly where all my money went. I can go back and go, ooh, I really didn't need to spend that. That was a waste of my money. I need to do a better job budgeting on that. Additionally, I don't have to carry cash all the time. And a lot of your credit card companies will offer you some type of an incentive. Like both of the cards that I carry offer a minimum of 1% cash back on every single purchase. And every month they're offering me 5% on particular things. Maybe it's restaurants, or maybe it's shopping, or maybe it's gas, or whatever. So this year, one of the cards I carry is Discover. This year, Discover has paid me over $500 to carry their card in my wallet, and I have not paid Discover a penny. The way that you don't pay the credit card company any money is if you pay your bill in full every single month, then there is no interest charge and there is no late fee or anything like that. But if you put $1,000 on that card, you got to pay $1,000 at the end of the month. If you do that, then you don't have any fees or any interest or anything, okay? And you can get airline miles or that type of thing, whatever it is, whatever incentive it is that the card is you might sign up for. So I look at that as they paid me money to carry their credit card. Now, there are pros and cons with that as well, because something that Dave Ramsey says that I absolutely agree with is it is a whole lot easier for me to swipe that happy little plastic card than it is for me to pull a 50 out of my wallet. There is something about having to pull cash out and hand it to somebody that feels totally different than just swiping a card. So it's easier to spend more when you're using a credit card than if you're using cash. So it doesn't do me any good if the credit card company is paying me 1 or 2% cash back and I'm spending 5% more than I would have if I was paying in cash. So you still have to work from a budget. You still have to be careful with what you're spending. Okay. So we talked about how you can take advantage of exponential growth with saving in a good retirement account as early as you possibly can and letting that grow for the long term. Don't touch that money, leave it there. We've also talked about the dangers and the pitfalls of somebody else taking advantage of that with you with credit cards or something else, so be careful with that. Now, each of those is an example of exponential growth, something growing at an exponential rate. There's also exponential decay, something that decays at an exponential rate. And that's what we're looking at in example number 10. For example number 10, it says, let Y represent the mass of a quantity of a radioactive element whose half-life is 25 years. After T years, the mass in grams is represented by Y is equal to 10 times 1/2 to the T divided by 25. And they asked me a couple of things. Okay, what is half-life? Half-life is how long it takes a quantity to cut in half. Like, have you ever wondered, like, why do I take Tylenol every 4 hours, but I'm only supposed to take ibuprofen like every 6 to 8 hours, and then, like, some antibiotics I take once every 24? I mean, who decides that? How do they know how often I'm supposed to take this? Well, part of it is based on that medication's half-life time. Like, let's say that we're talking about Tylenol, okay? Just a random example. If you took 200 milligrams of Tylenol, and Tylenol had a half-life time of 1 hour. I don't know what Tylenol's half-life time is, but let's say that it had a half-life of 1 hour. If you took 200 milligrams, then after 1 hour, you would have exactly half of that left in your system. You'd have like 100 milligrams. That's what we mean by half-life time. That's how long it takes for it to cut in half. So then after 2 hours, you've got 50 milligrams left, right? After 3 hours, half of that, 25. After 4 hours, half of that, 12.5. It's time for another dose, right? Because you went from 200 down to 12.5. There's not much left in your system, not doing much good. You need another dose, okay? Another place where we see this is like landfills. How come there are some things that I can put in landfills and some things that I can't? Radioactivity and hazard aside, of course. If there's something that has a half-life of 75 years, it doesn't matter if you only put this much in the landfill. After 75 years, this much of it is still there, right? Whereas if you put something that same size in a landfill that has a half-life of 2 days, it's going to be gone relatively quickly. So if you've ever tried to give blood and they ask you ahead of time, okay, what medications have you taken and how long ago have you taken them? It's so important that we get that accurate, that we get that right. Because let's say that you were sick a month ago and you got an antibiotic and you got penicillin. There's still residual of that in your blood, right, in your system. And so if they take your blood and they were to give that blood to someone who had an allergic reaction to penicillin, and there's penicillin in your blood that you give them, there could be problems, right? So that's why they ask you all of those questions. So we could sit here all day coming up with example after example after example of real world application of exponential growth and decay, so you can see what a relevant topic that this is, okay? So example 10, going back to our radioactive element that has a half-life of 25 years, it says, what was its initial mass when T is equal to 0? All right, so if I go through and the equation that they gave me was 10 times 1/2 to the T divided by 25. If I want to know how much was there initially, that's when no time has passed, right? So T is 0. So if I put 0 in for T, 0 divided by 25 would be 0. And then 1/2 to the 0 would be 1. So I would just get 10 times 1. I would just get 10. So you can see this formula was not given to you in the textbook, but this is our formula for half-life. And n sub 0 does represent the original amount. So you can see how we could have gotten that 10 for our original amount from either the formula or from plugging 0 in for T. All right, then it says how much of the initial mass will be present after 80 years. So we can go through and we can put 80 in for T. We're going to divide 80 by 25 to figure out how many times this thing got cut in half. And then multiply that by 10. and we find out that we've got 1.088 grams still present after 80 years. Okay? All right, so here is our homework from pages 225 to 226.